As we did our demonstration yesterday with the slinky and sent wave pulses from one part of the room to another part of the room, we saw that those waves carried energy from one part to another. That's the whole purpose of waves. That's what they do. That's the function of them. Waves carry energy from one place to another. When you jump into a swimming pool on one side of the pool and somebody on the other side of the swimming pool lying on an air mattress starts bobbing up and down, that's because they received kinetic energy from you. You didn't touch them, but your kinetic energy still was transferred to them by or via that wave. Waves are a means of transferring energy from one place to the other. Now they do this, as you saw in the demonstration yesterday, via the simple harmonic motion of individual particles within the wave. Remember that slinky, we sent a transverse wave, or that wave that looks like a water wave, from one end to the other, and you saw that little red piece of masking tape in the middle of that slinky going up and down. That was simple harmonic motion. You clearly saw simple harmonic motion in that piece of masking tape. That's what all the particles were doing. That's the connection between what we've been doing over the last several days to what we're now doing for the rest of this year. Wave motion, waves that carry energy from one place to the other, really are just simple harmonic motion of individual particles that carry that energy. Now, there's two types of mechanical waves. And by the way, when I say mechanical wave, I mean a wave that uses a medium, requires a material to go through. There's actually two kinds of waves, one of which we don't talk about until next year. The first kind that we don't talk about until next year is called an electromagnetic wave, and that's like light that travels from the sun to the earth through the emptiness of space. The other kind is called the mechanical wave that requires something to travel through. Air, water, some other gas, some liquid, some solid. Okay, that's what we're focusing on this year, is the mechanical waves, waves that require a medium, waves that require a material to travel through. You guys understand when I say that word medium, what I mean? The material that it travels through. Now, the two types of mechanical waves that we deal with this year are called transverse and longitudinal. These are the two waves that we demonstrated yesterday. The transverse wave was the wave where the particles move perpendicular to the wave. What does perpendicular mean? Pardon me? 90 degrees? Yeah, so if the wave is going this way, the particles are going up and down this way. The wave particles move perpendicular to the wave itself. Wave is going right, the particles go up and down. Wave is going up, the particles move perpendicular to the right in simple harmonic motion. Longitudinal waves, on the other hand, that second demonstration that I showed you yesterday, they're waves in which the particles move parallel to the wave. So if the wave is traveling to the right, then the particles are going to go right-left. If the wave is traveling to the south, then the particles are going to go south-north. Now remember, the particles don't transfer from one end to the other. They just go in their own little zone, their own little area, okay, but they move either parallel or perpendicular within that little area, within their little zone, in simple harmonic motion. Again, perpendicular, simple harmonic motion, or parallel to the wave in simple harmonic motion. Let's draw pictures of these waves. First one, what kind of wave is this? This is the one that looks like the water wave, right? Water wave, remember, isn't quite this kind of wave, but it's close. What is this? Transverse or longitudinal? Yeah, this is the transverse wave. Now notice what I have plotted here on this transverse wave. On the x-axis, this is an x position, so how far along the x-axis it is. And the same thing on the y-axis, it's a y position. In other words, a displacement, how big the wave is on the y-axis. I have labeled a crest. The crest is the peak of a wave. This would be a crest as well. Anything that's the top of that wave would be a crest. Okay, when you're surfing, you're riding the crest of the wave. The trough of a wave is like the bottom of a wave, or it's the valley. We'll call it the valley of a wave. We don't see these signs so much in Alberta. I'm not sure that I've ever seen it in Alberta, but when I learned to drive in Nova Scotia growing up when I was 16, one of the signs that we had to be familiar with when we wrote our test, our learner's permit test, and when we took our driver's test, and even after that as well, was a sign that said blind crest. I don't think I've seen it in Alberta. I don't think we have it here. But a blind crest meant basically you're driving up a hill, you see this sign that says blind crest. They're warning you in that case that watch out, because you're going over the crest of a hill, you're going over the top of a hill or the peak of a hill, and there may be somebody coming out onto the road on the other side. So maybe there's a driveway or something, someone's pulling out right here, and you can't see them. That's why they call it blind, because you can't see over the crest, the peak of a hill. Intuitively, when I'm 16 years old and going up in Nova Scotia, I knew what that meant, right? The crest is the peak of the hill. The trough is the valley. It's kind of like a feeding trough, right? If there's a trough in a barn, that's where the animals would eat from, this dip or this valley or this trough where the food would be in. The valley of a wave. The wavelength, well, we could simply define that as the length of a wave, but a better way to describe it is the distance over which the wave repeats itself. Now, the symbol that we're going to get for wavelength is a little bit weird. This is a Greek letter called lambda. It's like an upside down Y. L-A-M-B, lam, da. This is the wavelength, and it's going to be measured in meters. Typically, at least, that's a standard unit, just like any other distances measured in meters. Where are we going to label that? Well, we can label it a number of places. Tell me when to stop. I'm going to start right here. Label that as lambda. Tell me when to stop. Tell me when I've reached one complete wave, the distance over which the wave repeats itself. Okay, I'm going to keep drawing. You just yell out stop. Right there. That's the distance over which the wave repeats itself. Now, so is this. From the bottom of a trough, tell me when to stop. You missed it. Stop. That's the distance over which the wave repeats itself. That's one complete wavelength. Another one, we could say, well, from this spot right here, tell me when to stop. Stop. No. No, I didn't miss it. Oh, keep going. Oh, stop. There you go. That's one complete wavelength, the distance over which the wave repeats itself. Be careful. A lot of people are going to go from let's say from here to here. That's not a wavelength. That's a half a wavelength, right? You're going from here to here, the distance over which the wave repeats itself. So from the beginning of a crest to the beginning of a crest, or from the top of a crest to the top of a crest, and so on. The distance over which the wave repeats itself, it's lambda measured in meters. Finally, A, the amplitude, given by the symbol A, is the height of a wave. And it's related to the energy of the wave. You're not going to learn a mathematical analysis of the amplitude of a wave, but know that it is related, and not linearly related, but exponentially related to the energy of a wave. So, for instance, if you have a wave that is this high, that's a relatively low amplitude wave, but it contains a fair amount of energy. If you have a wave that's twice as high, then the energy of that wave is higher. What is it? Yes, it is actually. It's 4 times. The energy of the wave goes up exponentially with the amplitude or the height of a wave. It doesn't take that high of a wave to produce a lot of energy. That's why we don't see, by the way, waves that are 50 feet high, because in order to get a wave that was 50 feet high, you would need an unbelievable amount of energy in order to do that because of the exponential relationship. We're going to label the amplitude of the wave right here from this area that we call the equilibrium, which is right in the middle of the wave, to the top of a wave, or we could label it here as well. You don't want to label it from the top of a crest to the bottom of a trough. It's from the equilibrium to the top of a crest, or from the equilibrium to the bottom of a trough. Now this is our longitudinal wave. This isn't drawn real well, but it's the best that I could do on this screen here. The longitudinal wave you saw yesterday with the slinky, it consists of a series of zones in the spring, or whatever it's in, air or water or whatever it's in, where we have compressions, where the wave is tightly compressed, and then where it's stretched. So compressed, stretched, compressed, stretched, compressed, stretched. We call those compressions and rarefactions. The compressions would roughly correspond to crests, and the rarefactions would roughly correspond to troughs. So high density, or where the wave is really scrunched together, is a compression, and when the wave is stretched out, that's a rarefaction. And you always have alternating compressions and rarefactions. So compression, then rarefaction, then compression, then rarefaction. Remember the direction of motion of the particles. I forgot to mention this over here. The direction of motion of the particles for this one, you can see the wave is traveling this way. The particles are going this way, perpendicular. For this one, the wave is going this way. The particles are going this way, parallel to the direction of motion of the wave. We'll just define a compression as area of high density. What does that mean? Just more of the medium. If it's a slinky, then the slinky is scrunched together. There's more density in the slinky. And in a rarefaction, it's an area of low density. So we have the stretching going on here. The medium, the slinky, the air, the water, whatever, is stretched out. Okay. This is what sound waves are. Compressions and rarefactions, longitudinal waves. When you hear my voice right now, it's not like this sound particles are traveling from my throat to your ears. Rather, when I speak, my larynx or my voice box vibrates like this, and that causes compressions and rarefactions in the air that cause compressions and rarefactions in the air over there, which cause compressions and rarefactions in the air over there. Right? It's sustaining because one causes another, which causes another, and so on, which eventually goes into your eardrum. It's not like the particles in my throat. You don't have to worry about the bad breath unless you're up here. Going into your ear, it's these particles cause these particles to vibrate, which cause these particles to vibrate, which cause these particles to vibrate, which causes your eardrum to vibrate back and forth, which generates the sound in your brain. Was there a question over here? Is there a hand up? Yeah?
A transversal wave or
No, in a transverse wave, there's the crests and the troughs, right? The density would remain the same there. Yeah, so you're looking at the height of the wave versus the density of the wave. Okay, if I was to plot a graph on this one, be careful with this. This graph is like height versus length. This graph would be density versus length. If I was to do that, then it would look something like this. High density, low density, high density, low density. And it would look the same, right? But you have to understand that this isn't what you see, because you don't see density. You do see height and position. Does that make sense? Okay, let's spend a couple minutes talking about now the speed of a wave. Clearly, the speed of the wave represents how fast the wave is traveling. Remember, though, it is the wave, not the particles, because the particles are only traveling in their own little area, their own little zone, right? Either parallel to the wave or perpendicular to the wave in their own little zone. So when we talk about the wave speed, we're not talking about how fast the particles are traveling, we're talking about how fast the wave itself is traveling. Waves travel as long as they don't change materials or change media, as long as they don't go from air to water, or water to glass, or water to some other material. Water to wine, sure. Then they're going to travel at a constant speed. And if they travel at a constant speed, we can represent the motion by this equation. V is equal to d over t, the very first equation we learned this year. But we're going to tailor this equation to wave motion so that we can use a specific form of it in the analysis of waves. We can use this, but we can also use a more specific form of it. So let's do that now. V is equal to d over t. Can you tell me what the distance over which the wave repeats itself is called? The distance over which the wave repeats itself is called the wavelength. Yeah. So let's replace delta d with wavelength. The distance over which the wave repeats itself. Anybody want to take a stab at what the time over which the wave repeats itself is called? Nope. The time over which the wave repeats itself. The period. So that's going to be capital T. So we can make this lambda over t. And that's correct. Now, period is 1 over f, and that's usually the way we end up writing this in terms of frequency. So now we've got v is equal to lambda over 1 over f. Now, if we simplify that, it ends up becoming f times lambda. Lambda over 1 over f is the same thing as saying lambda times f over 1, or just f times lambda. This is what we sometimes call the universal wave equation. And it represents specifically the speed of a wave, related to the frequency of a wave, related to the wavelength of a wave. This one's also valid, but this is valid anytime you have constant speed. This is valid specifically when we have a wave moving at a constant speed. Now, one final thing before we do a question here, and before I answer your question. The speed of a wave can change, but only when you go from one medium to another. If I go from deep water to shallow water, a water wave will change speed. If light goes from air to glass, it will slow down, change speed. If sound goes from air to water, it will change speed. Only when we go from one medium to another, it'll change speed. And when it changes speed, it also changes wavelength. Speed increases, wavelength increases. Speed decreases, wavelength decreases. But this is important. Once the wave has been made, the frequency doesn't change. The frequency of a wave, once made, never changes. Even when we go from one medium to another, even when the speed changes, even when the wavelength changes, the frequency will not. If we have 10 vibrations per second in this wave, 10 crests per second, 10 troughs per second, even when the speed increases or decreases, you're still going to have 10 vibrations per second. All right, let's take a look at this example. It's a pretty straightforward one. Page 409 says, to generate waves in a stretched string, you oscillate. What does oscillate mean? Back and forth, oscillatory motion, oscillate back and forth. So if you take your hand on the slinky, on the stretch spring, and you go back and forth, you oscillate your hand back and forth at a frequency of 2 hertz. The speed of the waves is 540. What's the wavelength? Really easy question, right? Here's the frequency, 2.00 hertz. The speed of the wave is 5.40 meters per second, and we want to find the wavelength. What are we going to do? V equals d over t? That's valid, right? But we're going to use v is equal to f times lambda. How do you get rid of the f? It's multiplied by lambda, so we're going to take it to the other side by dividing. Lambda is equal to v over f. We got 5.40 meters per second divided by 2.00 hertz, which gives us 2.70 meters. So the distance over which this wave repeats itself, the wavelength, 2.70 meters. Now, given this speed, I could use this equation, v is equal to delta d over delta t, if I had the speed and t to find out how far the wave traveled, or given v and distance, how long it took the wave to travel. Okay, we can use that equation in conjunction with this. We don't have to in this question, but we can. Remember, given one of these questions, you're allowed to use this, of course. You're allowed to use this. Can anybody think of another one that may every once in a while be used in one of these? Speed, distance, time, speed, frequency, wavelength. How about this one? All three of these are valid. In this case, you only needed to use one, but be ready to use the other two as well. Okay, let's take a look at these questions, please, on page 409. There's three of them here. Let's look at number 2. Some of us are having a little bit of trouble with that, getting 13 kilometers for an answer, and it should be 6.5 kilometers. It says a submarine sonar system sends a burst of sound at the frequency of 325 hertz. Let's write that down. 325 is F. The sound wave bounces off the rock, so it's going this way, bounces off the rock, comes back in a time of 8.50 seconds. We have the wavelength is 4.71 meters, and we want to find the distance, right? Well, we're going to say for this one, v is equal to delta d over delta t, but we don't know v, so we'll find it. V is equal to f times lambda. So f is 325 times 4.71. Anybody have the value for that? 325 times 4.71. 1530.75 sounds good. So that's the speed of this sound wave in water. Jacob, this comes back to the question you were asking, we were talking about earlier, right? Speed of sound in water is about 1,530 meters per second. Hold on, guys, 2 seconds. Sub that in here, get a distance, and we get 1350 or something like that. We get 1350. What's wrong with that? What are we looking for? We're looking for the distance there. What do we solve for? The distance there and back. So we've got to divide that by 2. Please finish these 3 questions up for homework, please.